Okay, so moving on to chapter 3, first question we have to do is number 18, which is actually inside the chapter, it's not at the end. This is actually a really good question. It's asking for you to show electron movement, and it says to show the electron movement by showing the curved arrow notation. And this is really, really important that you get used to showing curved arrows because it is not going to go away. In fact, it's just going to get more and more intense as we go along through the semester. So this is an essential skill that you need to make sure that you really have a good grasp on, because if you don't, it's going to make everything else harder. So it's really important, and it's really worth it for you to put in the time and effort to really get a hang of this. So the first thing that we're doing is we're just going to show how electrons are going to flow to change the reactants to the products. So starting off on this first example up top, we have our carboxylic acid, this is acetic acid, and we have hydroxide. So these are our reactants, and the products are shown over here. The products are going to be this carboxylate and water. So the first thing you need to do is, whenever you're trying to draw arrows, is to take a look at the starting material, take a look at the product, and see what bonds have been broken and what bonds seem to have been formed. And so the obvious difference here is between the carboxylic acid and the carboxylate. So we used to have an oxygen-hydrogen bond, and it's disappeared for the product, so it's no longer there. So we know we need to break this bond somehow, okay? And then also looking at the hydroxide, this reactant is no longer hydroxide in the product. It's somehow acquired an extra hydrogen. So if we wanted to redraw this guy, it would look, something like this, where we have a OH, so we have two hydrogens that are covalently attached to this oxygen. So it looks like more than likely what's happened is we've taken a hydrogen, so let's say this hydrogen right here, this guy in pink. So we've taken this hydrogen and we're taking it more than likely from the carboxylic acid. Okay, so the way we would show this bond formation, so basically you are being asked to say how this new hydrogen-oxygen bond is being formed, this yellow bond right here. And so the way we're going to answer that is via electron movement. So the way that we're going to start this off is this oxygen has an excess of electrons. It is technically a nucleophile. Okay, so we're going to use a little bit of this electron excess to form a new oxygen-hydrogen bond. So the way that we show that happening is we're going to show electrons starting on the oxygen, and they're going to move over to the hydrogen. So again, the base of the arrow is indicating the electron start, and the head of the arrow is indicating the electron stop. So the electrons start here and they stop here. And we can't just leave it like this, because again, going back to our mantra, if we make a bond, we have to break a bond. That's definitely an effect here, because otherwise we would be, breaking the duet rule for hydrogen, which would say that we can't have more than one covalent bond to hydrogen. Okay, so right here, if we made a bond to hydrogen and we didn't do anything else, we would have one bond here and one bond here. So what we have to do is we actually have to break this oxygen-hydrogen bond. Okay, and we're going to take the electrons that used to be here and put them onto that oxygen. And we know that these electrons that used to be here are going to go to this oxygen because we can look at this negative charge on the resulting oxygen. So what that's telling us is that this oxygen is going to have 1, 2, 3 lone pairs, whereas it started out with 1, 2. And you can do the formal charge calculation, and it's really good if you want to do that. This is a calculation, again, that should be able to be done in your head very, very quickly. Okay, so this lone pair right here is coming from this bond right here, and this bond right here is coming from this electron movement right here. Okay, so that's how we're going to make a new oxygen-hydrogen bond, and that's how we're going to break that old oxygen-hydrogen bond. So let's see if I can make this even more explicit. This bond right here contains 2 electrons, and let's just say that those electrons are going to be right here. Okay. All right, so that's the answer to the first bit. Let's do the second question. So the first thing that you always want to do for these is, 1, look what's different, try to figure out what's different, and 2, try to figure out electrophile, nucleophile, because that's going to show you or help you figure out where to start your electron movement and where to stop the electron movement. Okay, so the main difference here is obviously for the cyclohexene, we used to have a double bond here, and we no longer do. So what we're going to do is also take a look at the bromine. So this bromine, to begin with, had a positive charge, and at the end of the day, it's neutral. Okay, so one way to get rid of this positive charge is to push some electrons onto the bromine, and we can also think about this double bond right here. So this double bond has quite a bit of, electron density on it. So in terms of talking about nucleophiles are any atoms or any bonds that might be electron rich. So this is a very electron rich region. This is a very electron poor region. So this is going to be our nucleophile, or Nu, and this is going to be our electrophile, or E. And you'll see this notation time and time and time again. Okay, so again, let's go ahead and try to start electron movement and stop electron movement. So because this is the nucleophile, we know that the base of the arrow has to originate on this molecule, and specifically the specific location of where there's an excess of electron density is right here on the double. So we're going to take the electrons that used to be here, and we're going to start electron movement here, and we're going to stop electron movement here on the bromine. So start and stop. We're stopping on the bromine because there's a lack of electron density here. And you can see that because of the positive charge. Okay, so again, what we're doing whenever we are making a bond is we have to use two electrons to make a bond. So the electrons that we're using are actually coming from this pi bond right here. Okay, so if you notice from the starting material of the product, we have a new bond formation happening. So we have formed a new bond between this carbon and this bromine. Okay, so we use the electrons from this pi to make this new sigma bond, and so this is a case where we can actually neglect that mantra of, if you make a bond, you have to break a bond. In this case, we don't really have to worry about breaking a bond because we're not, violating an octet rule for the bromine or the carbon. But the one thing you do have to keep in mind here is, overall charge balance. So thinking about the charge on the bromine has a positive charge, and the cyclohexene is going to be neutral. Okay, so here the book gave you that this carbon is positively charged, but what if you didn't have that positive charge? You would have to recognize that overall the left-hand side of the equation is positive. So overall on the right bit of the equation, the products have to have a positive charge overall somewhere. And so this is a case where it's really, really handy to be able to remember implicit hydrogens. So, this carbon right here, we're not showing it, but you need to remember that there's a hydrogen here. And again, we're not also showing it here, but it's really important to remember that there's a hydrogen here as well. So let's go ahead and draw those hydrogens out, because if you didn't, it might be really tempting to think that there are two hydrogens here and only one hydrogen here. But again, we're not adding any hydrogen, so we have to work with what we've got. So we have one hydrogen here, and we also have one hydrogen here. And so we know that this bottom carbon is going to be positively charged, because if we do our formal charge calculation, we can say that this particular carbon right here, let's call this carbon 1. Carbon 1 is going to have a charge of, if we do our formal charge calculation, 4 minus 3 covalent bonds minus 0 lone pairs. So that's going to be +1. So we know that this guy right here, carbon 1, has to be positive. And it's really, really important to be able to recognize when something shifts from being neutral to being positive. And it's a really easy thing to make sure that you get right, but it's also a really easy thing to get wrong. So it's, again, very, very important to make sure that you are rigorous in keeping track of what's charged and how many charges you have, because these little tiny things are going to mess you up later on. Okay. All right, next question.